this is what we stopped at last time. And from now on, I'm showing you the leg as well as the body we're gonna adjust. First of all, let's go to the leg. So, in order for you to use a simulation in CAD, here's something that you need to know. Remember last time when we did fixtures for everything? So let me open another file to show you the difference. This is our actual leg that should happen, including the servo motors and everything. But each servo has its horn, and we have our roller bearings at the back. So this assembly contains everything. If we do like this can move, this as well, and this. You got your 3 degrees of freedom in the leg. But this, as you can see on the bottom right here, it says underdefined. So if a system or whatever kind of thing that you're doing is underdefined, you cannot simulate it. So underdefined means it can move, as obviously stated. But if you want to simulate something pushing the leg, and you want to see if the leg will handle it or not, logically speaking, if it can move, then if you apply some force, it will move. So it won't tell you if it can handle it or not. If you want to see if something can handle a certain stress or a certain force, you want to hold it down and try to bend it, try to twist it, try to force it, do something to it while it's stable or while it's standing still or fixed somewhere. So in order for us to do that, I had to go right here and fix everything. As you can see on the left side, everything is fixed. The horns, I removed them because a couple of things with the simulation don't go well when you do I'll explain it. Give me 1 second, I'll show you. So if you go back here and we hide this, let's hide this as well. See, this servo motor, it has some gears. So the gears are very thin, to the point that this is the most thin part in the drawing. As well as if we hide this and this, but get back our horn and look at it from the inside, it's also geared to match the servo. So these things are super thin. You see these drawings, the teeth of the deer? Whoever drew this, I got this from GrabCat by the way, as you saw from the previous streams. Whoever drew this, it's amazing. It's great for drawing and for me to fit things together and simulate it as what should happen in real life. But that is a problem if you want to simulate, because if we go back to our simulation, let me just put these things back. Alright. Cool. So let's go back here. Now, if you wanna simulate something first, as we said, number one, we're gonna fully define it as shown on the bottom right here. Now, the reason I left the horns out, because if we start a simulation, here's how to do it. On the top left, let me see if you guys can see that. There you go. So, on the top left here, it says new study. You're gonna go to this tab, simulation. As you can see, I'm hovering over it. Simulation, and then on the top left, you're gonna click new study. After that, you're gonna name it whatever you want. I'll name mine, it's a one leg simulation, so I'll name it one leg. Doesn't matter the settings down there, just totally ignore it. So now you are on a different tab on the bottom here. Instead of the model, instead of the 3D view or a motion study, that's not now at all, but this is going to be a fun part. Now you have another tab called One LED. So the One LED is the study that you just initiated, and here you can adjust things that will not affect the main model. So if I go to parts, I can add parts, I can remove parts, I can let's say change material for something here, apply or edit material. I can do all that without affecting the actual model, the model here. This is not going to be affected. So when we want to simulate, we go over here, and here is the tricky part that we need to remove the horn for. Here you have to mesh this. So what a mesh does is basically you're breaking down these parts into very fine particles, so it can apply force to it, and it treats it, instead of treating this entire thing as one block, it treats it as very tiny triangles. So if you go to mesh and create mesh, here, mesh parameters, you see, you tell it what the triangle that it wants to consider is. So let me just put myself back here. Okay, so meshing here, as you can see, it deals with meters, so we're gonna have it as millimeters. Now we want to mesh this to be 3 millimeters. That's a nice thing to have, because here, this is the issue with the horn. You see, remember when I was drawing this and we said this is gonna be 5 millimeters thickness. If I had it as it was before, 8 millimeters, it wants to put inside here, like divide this into small triangles that's 8 millimeters thickness each. It cannot do that because it's 5 millimeters thickness only. It cannot put a triangle that's 8 millimeters wide inside a 5 millimeter part. Now, the issue is, the finer you go, the harder it is on the device to handle it. That's why people usually go somewhere here, which is, they just reset it, it goes to 8.8, and the tolerance here is like half a milli or something. But basically, if I try to, let's say, doing 3 millimeters, as you can see, it goes to fine instead of coarse. So even if I go this fine, if I had the horn or the servo motor present, it is way too thin. It is even less than 1 millimeter. It might even be less than, I don't know, less than 1 micron, which is like times 10 power negative 6. So now let's try doing it on 3 millimeters and see what happens. It is trying to simulate, but it's dying a little. I mean, it's trying to mesh, not simulate, but it's still dying a little. So I'm gonna close this actually, because I have 3 Solidworks tabs open. Yay! It did the triangles. First, I'll show you guys how it looks, but let me close this first. Oh god. Let's also close this until we need it. Oh my god, it's dying on me. Okay. Alright, now back to our simulation. If we go back to our one leg and redo the mesh. So create mesh. We did it as 3 millimeters. Now let's mesh. Alright, so now you can see what it wanted to do here. So it wants to put triangles inside of here. As you can see, we couldn't have done it with 8 millimeters because this thickness is 5 millimeters, as well as all of these, all of the grooves, everything here. This is not even like, this entire thing is 5 millimeters, and this is a part of it. So let's say that this was like 3 millimeters or something, and so on. Inside of these are all 3 millimeter wide triangles, and so on. So it treats it all as small triangles all beside each other, and then we do this. After you mesh, you want to tell it where it's fixed. So this robot is fixed as this bracket has a servo motor inside of it, and this motor is attached to the body. That's what's causing the weight, that's what's causing the force. But this entire thing is stepping on the ground, so it's fixed on the ground here. So if we want to fix it, you're gonna go to fixtures at the top, or at the bottom here you can see fixtures. So we're just gonna go to the top here and say fixed geometry. Welcome to the stream, Render, and thank you. I'll try to make it more understandable if possible. Alright, so we want to fix it at the bottom as we said. As you can see, if we hover on something, it tells you that this face is gonna be all fixed, meaning it's all on the ground or it's all clamped or glued somewhere. So as we said, this is gonna touch the ground here. So this is our fixture. This entire body and leg is gonna hit the ground here. And if you push the ground, it's not gonna move. So it's like it's fixed. And let's go and say yes to that. Now, technically, what we want to do is apply our force. As you can see at the top here, extra load advisor. You can apply a force, a torque, so it's like twisting something, or some pressure, apply gravity itself, or external load advisor. It's like a tab that will show you how to deal with these things. A bearing load, centrifugal force, temperature, and so on. So we're gonna go to force, and then here is the tricky part. Technically, this bracket is held onto the servo motor, which is held onto the body. If the body wants to fall off, so the spider is standing on its legs here as we fixed it. If the body wants to fall off, it will take the servo motor with it, as well as the bracket. So it's pulling this entire leg from the screws here. So this is what's causing everything to try and fall down. But if I apply the force inside the screws, sometimes it doesn't work. So we're gonna apply it around here. Let me show you first how it doesn't work, and let me show you how to fix. As you can see, like, it does the force perpendicular to the surface. So if we do this, it's perpendicular to this surface, and here it's perpendicular to that, and so on. So here it's gonna be perpendicular to the circular surface. Now we don't want that, because the screws are not hitting the sides. The screws are taking the entire thing and falling down with it. So we can click inside here. So we're gonna click all 4 places. Now you want it to be looking down. So you're gonna say, first of all, this is how much force is applied. So 1 Newton is like 1 kilogram of force. So if we do this entire thing for now, we say we're gonna do the entire thing 3D printed. So for now, let's say if it's all 3D printed and we go and check the weight, it's gonna say 6.5 kilograms, including all 6 leads, all our motors and everything. But the leads are not trying to take the body and fall. It's just the body affecting these holes. So if we remove each lead weight and just count the body, each lead is half a kilogram. Half by 6, that's 3 kilograms. So the rest of the body, including all components, is 3.5 kilograms. So worst case scenario, this robot, in order for it to walk, it's gonna have 3 legs on the ground and the other 3 are up in the air trying to move. That means our 3.5 kilograms have to be supported by only 3 legs, not the 6 legs. So let's say, for example, let's hit a number of 4 kilograms trying to be distributed by 3 legs. So we're gonna do 4 divided by 3. So each leg needs to hold 1.3 newtons, which is like 1.3 kilograms of force, which is newtons. Let's say worst case scenario, each leg needs to handle 1.5 newtons. So we're gonna do that, and then we're gonna go to the distribution. Let me just find it. I forgot where it was. Actually, that's not per item. That's total. 1.5. That's first of all. And yep, select direction. So it's inside here. Now let's click this face because we want it to be facing down. We want the force to be like the screws on the holes. So here's the hole, and this screw wants to take the body and go down. So we want the force to be perpendicular here. So we're gonna click this face and we're gonna say, you see these along the direction 1, direction 2, direction 3. So these are your X, Y, and Z according to this face that you just clicked. We can click that face and see what happens if we click this. So you see, it's going parallel to this plane. That's not what we want. We can shut it down as well. Click here. Yep, that's what we want. You see, it's going down. It's taking the force and going down. So this is exactly what we want. So we're gonna say yes, 1.5 newtons in that direction. Thank you very much. And it's total, not per item. So not per hole, not 1.5 newton per hole. That would be 6 newtons. That's not what we want. And we're gonna say yes to that. Now, you did your fixtures. Everything is fully defined. That's the most important part. The second thing you did is the fixtures, and then you did the forces. Now you're just gonna go up there and say run this study. Okay, so it says material not defined for one or more items. Let's check which material is not defined. We can go here. It's probably the bearings, right? So these are all, this says SWABS. That means if I go and apply or edit material, I'm gonna find it to be ABS already because I made sure that everything is ABS. Yep, okay, so it is all ABS, and this yield strength, actually that's a good thing that we opened that. So it wants to calculate the forces applied to this material, right? It needs to know what's the yield strength of this material, which means, to those of you who do not know these things, it means that if I bend this material, at what point or at what force Like, how much force can I apply to this before it yields, or before it deforms, meaning before it bends and cannot go back to its former position? So it's like you're bending a metal object, or let's say a plastic object. If a plastic object, if you're playing with a toy and you just bend it and it goes back to where it was, that has a high yield strength, or you didn't apply force enough to break its yield strength. So it needs to know what the yield strength of this thing is to know if the 1.5 newtons are gonna actually bend it or not. So here ABS does not have a yield strength entered in the material. So let's try making it acrylic. It has its yield strength here. So we're gonna close this so we can just mark all. So the tibia, the shaft tip, that's inside of here. The servo bracket, which is here. The two C brackets, which are these. And then the femur. The leg tip, which is the thing that we fixed to the ground. They all need to be the same material. Let's say acrylic, as we said. Apply. Thank you. Medium high impact acrylic, as we said. So I think these bearings are the issue. Let's do these because they have no material attached to them. Now, yeah, we can make it alloy steel. I'm not really sure what bearings are made of. Let me actually check, just double check. Oh, chrome steel. Okay. Is there chrome? Yep, chrome stainless steel. Made of that. Apply and close. So now you got your materials. Now let's try to run this again. Run this study. Fair warning, you need a good PC to do these things, because as I said, you don't want everything to overheat or not work properly. The more you put materials into this, so this is like dealing with a couple of parts here. Oh, it finally started. Cool. So we're just gonna put that to the side so I can explain things here. So it's dealing with this as one part, and then this 3, 4, 5, 6, and 7, like 6 the tip here, and 7 the shaft inside of here, and then 8 the ball bearing, and 9 the ball bearing, and so on. If you add more stuff, it's gonna get heavier and heavier, and the mesh is gonna take some time. I know that some projects need all of this to work, but the reason I'm only simulating one leg and not the entire thing, because my laptop will not be able to handle that. So I assumed, as you saw, I assumed that the weight is gonna be, as we said, 1.5 newtons on one leg and such, and then I worked with that. And here you see what happens when I try to put the load or the force in the holes for the screws. This is what happens. It gives me an error, and I tried so many times to fix it, but it doesn't work. So if you know the answer, please let me know. But for now, I found another fix for this. So it says numerical difficulties. The iterative solver stopped. Please check the boundary conditions and such. So we're gonna do here. We're gonna go to the forces that we applied, right click it, edit definition. And now, instead of applying it to the holes, we're gonna apply it instead of here, 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 or here. We're gonna apply it to the thing from the outside. These. It might still not work, but we're gonna check it out together. Now run this study, and we wait. If it doesn't already, like if you cannot see the mesh already happening, you can just right click the mesh here and click mesh and run at the same time. It will finish meshing and running at the same time, and it will show you each one and the percentage of it. Hopefully it goes well. I don't think you guys can see the errors that come up to me. So give me a sec to try and fix that. Not that. Ooh. No. Okay, much better. Alright. Let me see why this is not working. I think now it's fixed. Let me just grab it here. Yeah. Now you can see that. As well as you can see that. That's the error that's coming up to me. So the iterative solver stopped. Numerical difficulties, preconditioning failed. Please check module boundaries. Alright. Let's see how we can fix this. If I remember correctly, it's something to do with the settings of the simulation. I just gotta remember where to do it. Okay, so options. Let me see if you guys can see the options. You cannot. Okay. This. Not really sure why, but anyway, in the options, we're gonna go to, where is simulation? Yep, on the left side from here. Let me put myself on the right side. Okay, so on the left side here, you can see new study. If you click on it, it will show 3 options. I'm not really sure why it's not showing to you guys, but I can see 3 options basically, and the last one is study properties. Now let me see what I can do to fix that. Hey, now we can see it. There you go. So in this static, you can see options on here, incompatible bonding options, and then you'll see large displacement, and then you'll see use soft spring to stabilize model. We're gonna click that, as well as large displacement instead of compute free body forces. Then we're gonna click OK. We're gonna run this study. And remove that. Okay, it's working. Now let me put myself back. Of course, it's taken much longer, but if it works, then we did what we wanted. Anyway, how are you, Render? And thank you again for joining the stream. If you guys could hear my laptop right now, the fan is going crazy. Let me actually try to stop this. No, don't save the results, because you're taking too long. Let me do something here. Keep it compute free body, but use soft spring. And let's see what happens. Hey, excessive displacement were calculated. If your system is properly restrained, consider using the large displacement option to improve the accuracy of the calculation. Otherwise, continue with current settings and review the cause of these displacements. Click yes to solve with large displacement, no to solve with small displacement. First of all, we're going to do the no and solve with small displacement and see what happens. Alright, so it finished simulating, as you can see. Now let's do a couple of adjustments that will help you guys understand these things better. So here on the stresses, let's right click and go to chart options. It should switch to this screen right here. We want to see the maximum stress and where it is, and then we want to do this to be normal. As you can see, instead of scientific, have it to be float, and then in the definition have it to be, instead of Newton per meter square, which is Pascal, we want it to be Newton per millimeter square, which is megapascal. So these numbers can go down a little bit, then click yes, and now you can see that here we have the maximum stress of 0.89 megapascal. So in the displacement here, we're gonna go again to chart options. Again, maximum annotation, we want to see the maximum displacement. Also floating here, we want to see it in millimeters as it is. And then double click it so you can see actually where it happened. Oh god. It moved 20,000 millimeters. That's why it said there's an error. Now we know. But this entire thing basically moved without taking anything with it. So that's a connection issue. And we're gonna try and fix that later. But let's go to strain as well. Chart options. Floating. Show maximum. In the definition, there's nothing to click, so we're gonna keep going. Now, the entire reason we're doing this simulation is to see the factor of safety. If you're more than 1, that means you're not gonna break. If you're less than 1 factor of safety, meaning this thing or whatever material you're using, if it gets hit with that kind of force, it is gonna break 100%. So, as engineers, we want to stay above the 1, but as good engineers, we want to stay above 2 or 2.5 to make sure 100% that you are in the safe zone in case something more than what you predicted happens to the lead or to whatever material you're doing. So if I do a factor of safety and I show as, let's say 1.5, I am above the 1. My material is not gonna break if I get hit with 1.5 Newton force. if the body is that kind of weight applied to this kind of lead and so on. But if anything more than that happens, I do not know if my material is going to handle it or not, because I did not simulate it properly. But if I stay above the 2 or 2.5 factor of safety, and let's say 3 newtons hit my robot, I'm going to be safe because it's much higher than the one that I'm working with. So we're working for 2 factor of safety or 2.5 if we can make it. And let's see where we can see that. So at the top here, in the results advisor, you're gonna click down. You're gonna see an option that says new plot. In that new plot, there is an option that says factor of safety. We're gonna click that. Don't mind the options, just say yes. Just say yes. And here it is, factor of safety. We're gonna right click that, chart options. Now, instead of seeing the maximum annotation as always, we want to see the minimum. We want to see where is the least factor of safety, meaning if anything is below the 1 that we were talking about. First of all, we're gonna turn it from scientific to floating as well. You want to see the minimum. If our minimum is so low, wow. Alright, so our minimum is so freaking high, actually, not low. That makes no sense, because that means my factor of safety is way more than the 1. But this entire simulation is messed up anyways. It says that it's gonna be impacted and this is gonna move, but the entire lead is not gonna move. So there is something wrong with the simulation, which makes this number make sense now. So I'm supposed to be within the 1 to, let's say, up to 3 factor of safety. But this makes no sense. Anyway, we're gonna do something still. I was gonna see, like, if you're from 1 to 3, as I said, you would want this chart on the right here that says factor of safety 10 million gazillion something. That's the maximum. That's why everything is blue, because they're hitting that. But you would like that to be, my maximum does not need to be 10 gazillion. It can be 10. But it's not going to be 10 because my minimum is even lower than 10. So since it's rated, we're going to do 510 just to stay above the 506. Now, everything that's above 506, so 506 itself is the red part, and up to the blue part, which is 510. Now, let's say yes to that, and let's try to fix why this thing is not working. We can do it in a really simple way. It's not the right way, but it is a simple way. So, for the sake of simulation, we're gonna do this. We're gonna mark everything. We're gonna apply our material. Instead of acrylic, we're gonna have it to be steel. Where is the steel? Yep. We're gonna have it to be 10 IC 1020. And apply. Of course, since we changed material, we're gonna re-mesh and re-run. So right click on the mesh, it will say mesh and run. That's what we want to do, and let's see what happens. And if that doesn't work, there is still another fix. Again, not the right way, but it is a way. The mesh is done. And now it's running. it will ask us the same question, by the way, large displacement, and if you want to do yes or no questions, yep, there it is. Let me show you guys. That's the thing. Excessive displacement were calculated in this model. If your system is properly restrained, consider using a large displacement option. Improve the accuracy of the calculation. Otherwise, continue with current settings. And review the causes of this displacement. So this time, let's go with long displacement or large displacement calculations and see what happens. Okay, so this is actually starting to really heat up my laptop. So I'm gonna stop this here and do the other solution. We're gonna take that force, edit it. Instead of being on these faces, it's gonna be on this face. So here's what should happen. Once this bracket tries to fall, it will push this through these holes. So it's like basically it's pushing this here or this. So we're gonna do that. We're just gonna delete that from there. We're gonna do what happens if we want to push it from here for the total of 1.5 newtons as we were, and run. That's the second solution that I was talking about. You know the funny part? I did the first solution before stream. I already did this on my free time actually, and the simulation went great. It actually simulated without any issues. So I don't know what's going on right now, but I faced this before, as I said, and there are a couple of solutions for this. But the first solution worked for me fine. Not really sure what's wrong here. Are you guys the issue? Well, it's done. So 0.8 megapascals here. Don't worry about how it looks, but at least when something moved, everything else moved with it. So if you see from this angle, when this moved, and then this moved. So this connection is correct. The not correct part is that still when this moved, it didn't take this down with it. So the issue was between this part and the C bracket. So the servo bracket and this bracket. That was the issue. But if we go to our factor of safety, we can see that it's perfect. 212. And the reason being, this is all steel, so that's normal. But if, and let's also see the displacement, by the way, that's 0.007 millimeters, so that's almost nothing. Don't look at it as it is right now. I knew you were gonna look at this and say, dude, it moved a couple of centimeters. That's half a meter right there. But that's not what happened. It just looks like that because it's not fixed in anything. So the simulation just falls to the abyss here. But basically, it just moved 0.007 millimeter as stated here. This is the maximum it can move. But we're gonna do something here. Since it's starting to work again, we're gonna go back to the acrylic and see what happens. because it's the closest thing to the 3D printing or like woodworking or stuff like laser cutting as 2D stuff. But let's see what happens if we go back to it. Where was it? Acrylic. Yep. Apply to all. Close. And run. But first, let's go to study properties instead of large displacements. Since this is an 0.007 millimeter movement, it's not going to be a large displacement in that case. So that's why we can go back to our normal calculations and run this study. But as you can see, it is fixable, not the right way, but if you face an error, you can fix it just like that. If something is not working properly, or if one part is moving without being connected to the other parts, I'm 100% sure that my fixtures are correct, by the way, because I did this before, as I said off stream, and I did this multiple times until I figured out how to fix it as I'm showing you guys right now. But basically, if it's being wonky for any reason, if it is your fault or not your fault, you can just fix it like I just showed you right now. But we're gonna do our simulation. It's almost the exact same thing. I mean, this is gonna affect this, it's gonna affect this, so you can just skip one part that's not being fixed correctly with the other parts. If it moves and nothing else moves with it, as happens in front of you here. But you can just go to the next part and say, hey, this will move this anyway, so I'm gonna put the load instead of here, I'm gonna put it here, and keep your simulation going. So this is the stress analysis. Now we have 1.6 megapascals applying here. Now if we go to displacement, it moved 0.4 millimeters, so less than half a millimeter movement, and it's not even gonna move that half millimeter. It's moving because it doesn't see anything connected to it, but this is connected to the servo bracket, which is connected to the body. So it's like it's telling you that the entire body is just as it's moving, which is normal that it's moving like this, as we said, like its legs going up and down so the spider can move. It goes down half a millimeter. As it moves, it's not gonna move like this and keep its entire body leveled. It's gonna move and the body's gonna take the legs and move a little bit, so half a millimeter is basically nothing. And now if we go to the factor of safety, which is the entire reason we're doing this, you're gonna see it to be perfect. It's more than 1, but it's not great, because as we said, it's from 1 to 3. It shouldn't be this high. It's this high because I made the entire thing to be out of acrylic, which is not what we're doing. We're doing ABS, but we don't have the yield strength of ABS. But we can readjust the coloring here. It's colored like that because its minimum is 63, which is what we caught here, that this is going to be the weakest part. If it breaks, it's gonna break from here, but it's not gonna break because it's way above the 1. And the highest is 510, which makes no sense at this point. So we're just gonna go to chart options and say 65. So we're getting closer to what we want to see, which is the 1. Normally you should, if it did from 1 to 3, as I was saying, you should have your maximum to be 10 maximum. So your factor of safety is from 0 to 10, or whatever minimum that you get to 10. So we're getting there, we're getting closer bit by bit. So give me a second, I'm gonna check if I'm able to find the yield strength for ABS, put it in manually, and then actually I think I did that before. Let me recheck that here. Let's do that. Mark all, edit material, you can actually, let me show you this, guys. This is a cool trick to have. Let's see here. Okay, so in these materials, if, for example, what happened to us here, you click on ABS, oh, there's no yield strength, but I want the exact same parameters, I just want to edit this, you can just copy it. So right click, copy, and then go down to your custom materials and paste it somewhere and edit the yield strength yourself, as I did here. So we're gonna choose this, and this is also for PLA, and this is normal plastic. I didn't put the yield strength because I never used it. This is rubber stuff for the tip, but we're gonna go for ABS and say apply here. This is our custom made ABS, so let's run this study. I basically, again, as I said, I already did this before off stream, but it was weeks ago that I forgot how to do it, and I forgot that I actually had the ABS yield strength in the system. But basically, I just went online, checked what the ABS yield strength should be, what's the norm, what's the average, and then I found that number. I did this average myself because I found it to be from 30 to 50 something. So I had it as 35,000, as you can see, or 350,000. I don't remember the number that we just saw, but basically that's what I did. I searched what the ABS should have as a yield strength, and I took the average of all the findings that I had and then entered it in the system. And now we're gonna see what actually should happen in real life. So in real life, we should have a 1.784, so approximately 1.8 megapascal force here. Our factor of safety should be the drumroll. Let's go. 49. Cool. So it's getting less and less. And our displacement also around the 0.5 millimeter. So that's actually great. Now, this is how you simulate the leg. So I'm gonna continue this offline actually, but let's go check the body out. Basically, I just wanted to show you guys how to do the simulation, and I'm glad actually that I encountered these issues to show you guys the fixes for it. But this is basically what you do to simulate the leg. But let me actually show you something very cool. Let me transition to this. So when we found out that these things, or basically simulations and 3D printing and those numbers that you saw, we went out and asked how much would it cost us to actually 3D print this, and the number was humongous. So we wanted to do our kinematics for the leg. I'm gonna do a little bit of a reveal here, something that you shouldn't see now, but I'm gonna show you anyway. Alright, check this out. So we wanted to do the kinematics of all of this, which means that we wanted to see how the leg moves, how it goes out of the ground, how each servo moves, the power electronics of it all. So we needed to actually put it on a leg to test first before we 3D print anything and pay a hefty price. So we did a 2D model for it all and printed it as wood, as you can see. Ta-da! This is the lid! My lid! Alright, so here's what you need to see. In the simulation, this is the servo that is put inside the bracket that didn't work in the simulation. We did it with this, it's broken, of course, because we did a couple of simulations. A lot of things didn't work out well, and we're still testing, of course, but it broke off of us. This was supposed to be clamped to a table, and it's like it's being clamped to the body of the robot. And this is, let's say this entire thing is clamped right there to a table or the body. This is the servo that helps it go sideways, and then this is the servo for the tibia. Here it is. And then, or the femur, I think. Anyway, these are the C brackets, this and this. And then you got this servo is the one for the last part. Don't remember, femur, leg, whatever. Yeah, that's the tibia, that's the femur. So this servo, the last one, helps it go out and in. And this one helps it go up. And then this one helps it go sideways. This is the leg that we made. But still, we're working on a lot of things to improve. I know that there are 2 holes here. So this is all actually, by the way, I got the idea from Japanese like inventors and stuff like that. So basically, in Japan, people just don't use screws that much because they're great with woodworking and puzzles, just clamping in together. So I took the same idea, very simplified, very simplified, and I just had it here. So I don't use any screws to put these together. This is just built here, so it can go in, and it's made with such high precision by the laser cutter that these holes fit this thickness so that it can actually just go in, and that's it. If you try to pull it apart, you're gonna put a little bit of force into it. It's not easily pulled apart. And if you can see here, these 2 holes, I made them so that I can build something that's, because building a big part out of 2D material is kind of hard. But these 2 holes are supposed to be where the trigger sensor will be put, so that the shaft can be put here, a circular shaft can be put here to tell the trigger sensor that, hey, I touched the ground, stop the motors, don't force the leg down more than that. But basically, this is where the trigger sensor will be, and it needs to be put in somewhere here, basically, and the shaft will press from this area. As I said, a lot of things are gonna be still adjusted and fit better than this, but for now, this is what happened. And let's go back and adjust our body a little bit, then call it a day, basically. Alright, so in this body, what we want to do is this. Nope. Okay. Let's do this. Thank you. Let's edit that sketch. And let's have that facing this way. All right. Okay. Let me see exactly what I'm trying to do here. Because I have the vision in my mind, I just don't know the what's it called? The measurements. So let's evaluate this. So this is 62 millimeters, let's say 70. So we can have some breather. So I need this. Nope. Yeah. So this should be 7 centimeters. As well as this. And I'm trying to have it from this side be 6, just like the one above it. Now trying to have this on here. Yep. And then this. And this. Yeah. Trying to have that to be 3. Nice. Okay. Now I want this here. Yeah. Let's have it to be 3. Nice. Okay. You're gonna get it in the end. Let me shoot. Let me shoot. Oh yeah, or that. Thank you. We're gonna have that. I think you guys can already see that it's sliding, right? Whoop. And this should be 6. Thank you. Okay. Kinda what I wanna do. Of course, it still has adjustments. This could be rounded, as well as this, and so on. Um, Yeah, it would be a lot better than this. For this to naturally go down here. Huh. Let's do something. What do we want to do? This can go. This can be 20. This can be 40 in that case. Yeah. But let's first undo both. Alright. This actually needs to be 7. Let's define everything else so it doesn't move. Yep. Now the question is, why did this move? Hmm. Yeah, it's getting fixed. Nice. I was scared for a sec. Okay. Now that these cannot move, let's see about the rest. Uh-huh. Let's first do that. Okay. Now, let's do something cool. This is gonna be like that. Now, let's do this. Okay, exactly what we wanted. And all of this to be 40. Not what we wanted. Okay. Yep. That. Thank you. Yeah, it's getting a little bit better. This can all just be shifted inside, which is gonna have this to be shorter. But for now, that's actually great. So let's keep that like that. It's gonna mess up our entire assembly, but that's the process. Oh, I see you. Anyway, let's go check out our assembly. We're gonna have so much errors. Yep. Well, since you guys already know how we assemble things and you guys already know how I'm gonna fix this, I'm just gonna remove all of these 4 legs and reassemble them so that they can have better constraints, as well as the camera, the LiDAR, and everything inside, which is this. So you guys already know how I'm gonna fix this. Well, with that, I'm gonna end the stream right here because we just hit the 2-hour mark, and that's it for me today. I hope you guys enjoyed, and this is gonna be compacted into a better VOD on YouTube as well, so look forward to that. And for now, thanks for joining me, and have a lovely day.